what we want to talk about today is some basics about digital and input and output, because while it's nice to be able to program this microcontroller, we probably want to interface it with some other pieces of hardware other than just a laptop if we're going to use it for a balloon payload. So we usually use I/O to stand for input and output. So, and digital, as we discussed last time, means that it's a on and off value. So if you were to look at the signal on a oscilloscope or as a function of time, it would look like a bunch of squares, and it would look, or steps. This is as opposed to an analog signal, which is a smooth, continuously varying. And most modern electronics use digital I/O, especially the microcontroller, because basically to do any sort of computational operations on it, you need it to be digital, because all of our modern computing infrastructure is digital. You could actually build analog circuits to do some calculations, but basically that means they can only do one sort of thing. So you could build a analog integrator, which would add up a signal, but that circuit would only be able to do that. Whereas with a computer that you can program, but because of all of that programming and instructions is based on digital logic, to do stuff with the signal, you need it to be digital signals. So the sort of things that you would consider digital I/O would be, simple indicator lights. You just turn those on and off. You could just be turning a motor on and off. You could be opening a valve. Most of your communication is going to be digital. It's some sort of pulsed wave that will transmit the signal, but it'll be square steps of on and off. You can, obviously you can read a signal if it's just on or off. Most of your user controls and switches, again, those are on and off. You are either hitting the S key or you are not hitting the S key, right? There's no in-between value there. Obviously, you would need a whole bunch of digital inputs for all of the different ones, but that's not too hard to do. So as I said, the difference between a digital and an analog signal is that the analog signal is smooth and continuous, right? So it's looks more like what you think of when you just think of a bunch of waves, whereas the digital signal is a bunch of on-off pulses. You have nice sharp edges, a clear difference between the on and the off value, and then a obvious point in when it turns on and off, these nice sharp edges. So obviously the real world is not digital. Most things are going to vary continuously. So how do we change digital signals from that? Well, that's why we have binary values, right? We already saw during the programming introduction, you can represent numbers as with a bunch of binary digits. And for actual digital signals, we assign a particular voltage threshold to be anything that and below is 0, and anything and above that is 1. And we usually also call that true and false, where 1 is true and 0 is false. So how do you, if you have a voltage, how do you know if it's a 1 or a 0? And what you do is whatever you're using has a logic level standard. It's basically the people who have manufactured the circuit have agreed that above this value is a 0 and below this value is a 1. They're the levels that tell you what logical value it is. And so this is just an example of the Arduino's logic levels. And you can see there's actually a bunch here with different names. So we'll actually talk about what they are. So obviously the highest voltage here is 5 volts VCC. So VCC is usually used for your supply voltage. So that means this whole thing is running on a 5-volt system. And sometimes you'll see these other voltage quoted as either fractions or percentages of VCC. But in this case, we're giving actual values. So then the next value is VOH, which is voltage output high. So this is the lowest voltage the circuit will output when it's a high. So that means when it's outputting a high, the voltage will be somewhere between VCC and VOH. The next one is VIH, which is the minimum input voltage to be considered a high. So when the circuit is taking an input, everything above VIH will be considered a high. And so obviously one of the reasons this is a little bit lower than this is you do have, small resistances, even if you don't mean to, that could potentially cause your output voltage to drop a little. So that's why usually you see the input voltage being slightly lower. Next, we have the VIL, which is the voltage input low. So this is the highest voltage that will be considered a low input. So everything below this 1.5 volts is going to be a 0. And then finally, you have voltage output low. So this is the highest possible value that will be output for a low voltage. And then finally, you have ground, which is 0, but that's 0 by definition. So we're measuring all of these voltages from whatever this ground is. And you'll notice that there is a bit of this dead region in there. So that's not going to be considered either a high or a low. And if you actually have that as a input to a logic circuit, it might act weird. So basically, you should never have a signal within this range within a logic circuit. And so one of the reasons you want that is because basically it'll cause you to ignore your noise. That's what gives you those nice sharp edges when you go from high to low. Yep. So there's actually a few different types of digital IOs. So one thing to note is there's usually 2 types of current that we talk about. Direct current is where the current is only flowing in one direction, and alternating current is where it's flowing in both directions. You may also hear it referred to as unipolar, i.e. it goes basically from 0 to positive, or you can go from, or you can have bipolar, which it goes positive and negative. And then there is another type of signal that we talked about for digital signals that on the pulse width modulation, which you recall there was a number of pulse width modulation pins on the Arduino, and we'll talk about what those actually do. Right, so in our unipolar case, we only go between 0 and 1, or 0 and positive. So when the voltage is at 0, it's considered a, when it's at 0 voltage, it's considered a digital 0. When it jumps up to the high voltage, in this case, we're just showing 5 volts, but you know, there's other logic levels. This could be 3.3 volts. It could be 12 volts. It's considered a 1. So one thing to note is that when your signal is off, it's considered a 0. So you don't really have a way of telling the difference between I'm not sending anything and I'm sending a 0. So because of that, sometimes you will see bipolar signals, which has basically, you have a positive voltage value for the ones and a negative voltage value for the zeros. But then you can also have a neutral value that is basically just like I'm idle. And in this case, you'll see two different types. This is a non-return to 0, so it just transmits the 0 or the 1, and then it stays at that value until the next value is transmitted. But then you also have return to 0 signals, which you transmit the 0, and then you go back to the neutral 0 voltage, or you transmit the 1 and then drop down to the neutral 0 voltage while you're sitting idle. Right. So then the other, another type of digital signal that we talked about, I said, was this pulse width modulation. And what you're actually changing is, it's still a digital signal, so it's still a 0 and 1, but what you're actually doing is varying the length of time that it's on. You're modulating the width of the pulse. And what this does is it allows you to basically get a analog output out of your digital signal. So you can use that to control the brightness of something. You can change the speed of a motor, you know, or you can change the direction of a servo, which is just basically a small pivoting motor. So based on the width of the pulse, you can set it to, you know, 90 degrees, 10 degrees, 15 degrees. The point is you have basically a variable width output. So how does this work? So like I said, you still have a 0 and a 1 value, right? But you have a repeated pulse that is of a certain length. In this case, we're calling that T. What you then do is have it on for a certain percentage of that total T. So in this case, it's at 50%, and we call the time that that's on the duty cycle. But there's no reason I have to keep this at 50%. I can vary this anywhere between 0 and 100. So what you can do on the other end of this is basically have an averaging circuit that gives you an average output. So when this is at 50%, I would then average over that and get 2.5 volts. But I will point out, you need to have that circuitry that does that averaging, because this is still just a digital signal. So a lot of times in this case, right, it's you could control the light where the brightness varies. At 100%, it's at its brightest, and at 0%, it's off. And if I change that, it will change the brightness. So, you know, just like we said, the zeros for an Arduino is a unipolar voltage, so it has zeros and ones. So when the voltage is low, you know, it's considered a 0. But we probably want to know the difference between I have a 0 at an input versus I don't have anything connected to an input. Also, I'm sorry about this slide. That should say Rogue, not Rouge. I will correct that. But basically, I want to add circuitry to our input or output pins so that we can tell what we're actually outputting. So one way you do this is through what are called pull-up and pull-down resistors. So what that means is basically your I/O pin is always connected to either a positive voltage or a ground. But I put a resistor between them, one, to make sure I don't just overflow, have the current exceeding out, especially if I'm using this, this pin as an output. If this is high and I just connected straight to ground, well, then there's nothing to limit that current, so I'm going to pull as much current until I damage that pin. But if I put a resistor there, that will prevent that. So if I connect a I/O pin to a positive voltage through a resistor, that is called a pull-up resistor. And that means if there's nothing connected here, this will be a high value. And the reverse is where I have a I/O pin connected to ground through a resistor. That's called a pull-down resistor, and that gives me a 0 when nothing's connected here. And that's important because if I didn't have that and I just had this I/O pin connected to nothing, which is called floating, basically you might get all kinds of weird voltage values, which means you'll have all kinds of strange inputs if you're trying to interpret that. Right, so like I just said, pins can be in an unpredictable high or low state, sort of depending on a lot of hard to know variables if they're not connected to anything. So if you have something that's behaving weirdly, one of the causes may be that the input pins that you're using are not connected to anything, they're floating. And because of that, you want to, like I said, use this pull up and pull down resistor. One thing that is important to note is usually you don't really care what that resistor is. It's mainly there to prevent you from having a almost zero resistance and drawing too much current through the pin. So that means, basically anything from 1 to 100 is okay. There can be impacts depending on what sort of circuit you actually connect to the I/O pin if you start worrying about timing, but that's, you know, something to worry about when you're designing that circuit. So just to review, these are all of your Arduino pins. One thing that's important to note is basically that every single one of your pins on the Arduino is a digital pin, even the ones that are analog. That just means they are digital pins that can also be used for analog outputs, or analog inputs, sorry. You also have, as we discussed, your pulse width modulation pins. Then you also have your serial ports and your I2C pins. And then one thing to note is, depending on which version of an Arduino you have, there are these 6 central pins, but those are actually connected to pins 50, 51, and 52 in the center here, if I remember correctly. Also, you have basically a 5 volt and 3.3 volt supply. You have several ground pins, which are all connected to each other. Yep, so as I said, you have multiple ground pins. In fact, there's 5 of them. They are all connected to each other. So if you need to have a ground on the Arduino, basically, which you will often need to do, because when you're measuring voltages with the Arduino, you're always measuring voltage with respect to some 0 level. So you want to connect the grounds of the things together, so you're starting at the same 0 level. Like we talked about, there is a input voltage pin which supplies power, but that does not go through the regulators. So you want that 5 volts that you're supplying there to be very reliable, so you don't damage the Arduino. You have a 3.3 and 5 volt output. These are mainly used for supplying shields. This reset pin is basically the same thing as, so connecting that to ground is the same thing as pushing the reset button. And that's mainly there so that if you have shields that cover up the reset button, you can still have access to that reset function. And often many shields will have their own reset buttons that connect through that pin. And then finally, there's a I/O reference that is the reference high voltage of the I/O. So for the Mega, it would be, again, another 5 volts. But one thing to note is that's not designed for power. So you don't want to supply circuits off of that. That's just to give you what the high level, the voltage level is. There are also some 3.3 volt Arduino boards. So in that case, they would have a 3.3 volts at that I/O ref pin. Again, you have the pulse width modulation pins, and then you have 4 sets of serial ports. So these are usually, these are called serial 0, 1, 2, and 3. It's important to note that serial 0 is also the same thing that is on the USB. and when you call that within the programming, it'll just be serial. So I was actually using this serial 0 port in the earlier programming activity, whereas these ones will be serial 1, serial 2, serial 3. There are these 2 dedicated pins for I2C. Actually, we're talking about these ones here. And that is for communicating with other circuits through that I2C or I2C protocol. You have a clock pin and a data pin. So basically there's a synchronized clock pulse, and the clock pulse tells you to look at what the value of the data pin is when the clock pulse happens. We'll talk about that later. So then there are, so this is on the bottom header row. So there's 3 more pulse width modulation pins, and then there's these 4 dedicated pins, 50 through 53, which are used for another communication protocol, which is called SPI. And that protocol uses what's called a master and slave system. So there's one master device that talks to all of the other individual all the slave devices, and they do not, all the slave devices do not talk to each other. So there's an input pin for the master that the slaves listen to, and the reverse. And again, you have a clock pin for synchronizing those signals. And then there's what's called a chip select pin. So if you have multiple slave devices, the way that you switch between them is you'll have a different select pin for each of them, and they will only listen while the appropriate select pin is high. So when you use an I/O pin, they can either act as an output, right, or an input. Usually when it's an output and it's high, it's acting as a current source. You know, you'll have some sort of load and then a limiting resistor to prevent you from drawing too much current, because, you know, this may be something like just as simple as an LED. Well, if I just have an LED hooked up to ground and I apply a positive voltage, there's not really anything limiting the current through it, and I will draw more and more current until I either overheat the LED or the pin, you know, depending on which one will break first. So as I said, this is, you have it connected through a load and a resistor to ground. Sorry. When it's high, you flow through the load to ground, and it's acting as a current source. When the pin is low, there's basically, this is at 0, this is at 0, so there's no current flow whatsoever. And usually the way you use this is you turn the pin high to activate whatever this load is, and you turn the pin low when you want it off. So when you want to use it as an input, usually the pin is acting as a current sink. The current flows from some other source and into the pin. So when the pin is low, you go through the limiting resistor and through the load, and it turns on. When the pin is high, this and this are at the same value, so you basically do not have any current flow. And again, you're going to want a limiting resistor to prevent current, high currents from damaging either your load or your I/O pin. So this is sort of the reverse of the other one. You can again use it as a control, but now a low would turn on the load and a high would turn it off. So just as an example, like I said, you could, a pretty simple example of a load is just an LED. So if I'm using my I/O pin as a source, I would put the LED here and the limiting resistor here, and I'm connected to ground. Now, a key thing to note is it doesn't really matter. I could swap the position of the LED and the limiting resistor, and it would function exactly the same. What makes it a current source is the fact that I'm connected to ground on the other end of the I/O pin. And then conversely, I could also have the I/O pin acting as a sink. It's functionally the same thing, except the operation is reversed. On the source here, the LED turns on when the pin is high. So when I have 5 volts or true at the pin, LED is on. In this case, I have the LED on when the I/O pin is at low or false. So this is sort of the default configuration of the pins. They are normally set as inputs. If you want to use them as an output, you need to do a declaration. A key thing is the specification on the maximum current for these pins, which is 50 milliamps. So to actually do things with these pins, we need to know what the programming functions are so we can actually program them. So the 3 pin commands that you're interested in are the pin mode command, the digital write command, and the digital read command. So the pin mode tells the Arduino, I want this pin to be an input or an output. So like we said, the default configuration is an input. So if I want to use them as an output, I definitely need to have this call. The digital write command is what's used to switch an output pin to either high or low. And the digital read command pulls what is on the pin. So it checks the value of the pin. Is it high or low? And that'll return a true or a false. So just as an example of some code here, this is going to set a particular pin 13, to an output pin. It'll turn it on for a second and then turn it off. So if we go through, we have our pin mode and setup. So I'm calling the pin mode, and then within these parentheses, I need to pass the arguments. I tell it I want pin 13, and then comma, and you'll see this is output it all in caps letters. So that is actually a constant keyword in the Arduino that is basically a predefined variable within the Arduino software. So then once I go into my loop, I see digital write. Again, I want to tell it which pin, and I want to tell it the value high or low. So high and low, again, are constants, just like the output here. And in between those steps, I have waiting for a second. So I set pin 13 high, I wait for a second, set pin 13 low, and wait for a second. We're not really going to go use this too much in the activities, but it could be something that's useful for your payloads. So you would like to probably know how to use the pulse width modulation. So it's the same sort of thing, except you have an analog write. Obviously, you can only send to the only use it on those designated pins, but it's the similar sort of thing where when you call the write, you tell it what pin and what value I want. But in this case, because you have a variable width, you can go from 0 to 255, where 0 is off the entire time, and 255 is always on. And with each individual step from 1 to 255 is going to increment by the appropriate percentage. Like I said, basically you can only use it on the pins. And that is it for today's lecture.